You know, we live in a world that is completely obsessed with speed. Every part of our digital lives is built on processors doing billions of things every single second. But what happens when that's just not fast enough? You can't just keep trying to make your software faster and faster. The real answer is this incredible high-stakes hardware arms race, a battle fought not with steel, but with silicon.
And if you want to see where this fight gets truly insane, look no further than high-frequency trading. We're talking about a world where a single nanosecond, that's a billionth of a second, is the difference between making a fortune and losing one. This is a place where the actual speed of light starts to feel frustratingly slow.
For years, trading firms pushed software to its absolute breaking point. I mean, they were hand-tuning code, bypassing the operating system, just squeezing every last cycle of performance out of their CPUs. But eventually, they hit a wall, a hard, physical wall. So what do you do when your trusty processor just can't keep up anymore?
And this, right here, is where our story really begins. This relentless chase for speed forced engineers to look past software and start rethinking the hardware itself. They needed a whole new class of weapon for this nanosecond arms race.
See, the fundamental problem with a CPU is that it's a generalist. It's designed to do everything pretty well. But in high-frequency trading, pretty well doesn't cut it. You need to do one thing: grab market data and make a decision at an impossible speed. You can't have unpredictable delays from the operating system or a cache miss slowing you down. The CPU, for all its power, was just too slow and too unpredictable.
So to understand the solution they found, we really need to map out the battlefield, because not all chips are created equal. They all exist somewhere on a spectrum, which is defined by a fundamental trade-off that every hardware designer has to wrestle with.
And this chart illustrates that trade-off perfectly. On one end, you have maximum flexibility, the power to run any kind of program you can dream up. And on the complete opposite end, you have raw, specialized, face-melting performance. You can pick your spot anywhere along this line, but here's the catch: you can never have the best of both. So, let's meet the players.
So all the way over on the flexibility end, we've got our old friend, the CPU, the Swiss Army knife. It runs your browser, your games, your spreadsheets. It does it all. But because it's a master of none, that versatility comes with a cost, a lot of overhead. And that overhead is an absolute killer when every nanosecond is on the line. Okay, let's take a step to the right, towards performance. Here we find the GPU. And the parallel army analogy is just perfect. Instead of a few super smart generals like a CPU, a GPU is made of thousands of simple foot soldiers. They all do the same basic task at the exact same time. It's amazing for things like graphics, and as we'll see, for crypto mining. A little more specialized, a little less flexible.
All right, now things get really interesting. This is the FPGA, the Lego set of the silicon world. Imagine a chip that comes from the factory as a complete blank slate. It's just a sea of generic logic blocks that aren't wired up to do anything. You, the designer, get to connect them all together to build a completely custom circuit, one that's perfectly designed for your specific problem. And then, at the far end of the performance spectrum, you have the ASIC. This is the custom-built Formula One race car. It is designed from scratch to do one thing, and one thing only, faster and more efficiently than anything else on Earth. The trade-off? Zero flexibility. An ASIC built to mine Bitcoin can only mine Bitcoin. It literally can't do anything else.
So let's go back to that Lego set, the FPGA. How does that actually work? I mean, how can you reshape a physical piece of silicon after it's already been made? It's a seriously mind-bending idea, but it's the absolute key to this whole story.
Well, it really boils down to three main parts. You've got the Configurable Logic Blocks, or CLBs. Those are the actual Lego bricks. Then, inside each one of those bricks, you have these tiny little programmable brains called lookup tables, or LUTs. And finally, you've got the programmable interconnects. Those are the wires that let you connect all those bricks together in any pattern you want.
This quote right here is just a fantastic way to understand what a lookup table does. It's basically a tiny truth table baked into hardware. You give it a set of inputs, and it instantly looks up the correct output you pre-programmed. By changing what's in that table, you can make it act like any basic logic gate you want. It's literally a hash map in silicon. So, and this is key, programming an FPGA isn't like writing normal software. You're not writing instructions for a processor. You are literally describing a physical circuit using a special language. That description then gets compiled or synthesized into a map of how to configure all those Legos and wires.
And the final output, this bit stream, is a file that physically reconfigures the connections on the chip. You are creating custom hardware using code. It's incredible.
Okay, so now we get it. We've got our spectrum of hardware: CPU, GPU, FPGA, and ASIC. So how do you actually choose the right weapon for the right fight? Let's dive into a couple of real-world battlefields.
Let's go back to high-frequency trading. Here, the FPGA is the undisputed king. Why? Because you can build a hardware pipeline that takes market data straight from the network cable. There's no operating system getting in the way, no random delays, no context switching. Every single clock cycle is predictable, giving you what they call deterministic nanosecond-level latency.
And the results, they're just staggering. One firm saw a 40 times improvement when they switched from a super-optimized CPU setup to an FPGA. Their latency dropped from about 10 microseconds, which is already insanely fast, down to just 250 nanoseconds. In that business, that's the difference between seeing a price and actually getting that price.
But here's the twist. FPGAs don't always win. In the big war for crypto mining, they actually lost out to GPUs. And the reason is fascinating. Algorithms, like the one for Ethereum, were deliberately designed to be memory hard. This means they need access to huge amounts of data, which requires massive memory bandwidth. Well, GPUs, with their super-fast gaming memory, were perfect for that, while FPGAs just couldn't keep up. It was a clever, intentional design choice to try and keep specialized hardware from taking over.
So when do you go all the way to a full-blown ASIC? Well, take a look at Google's tensor processing unit, the TPU. Google saw that running AI models was going to be a gigantic piece of their data center workload, so they just built a custom chip, an ASIC, that does only one thing: run neural networks super efficiently. Their target was to get 10 times better performance for the cost than a GPU, and they did.
And this brings us to the future. We've seen this incredible spectrum of powerful, specialized hardware. But there's always been one massive barrier that's kept these more exotic chips from going mainstream.
And that hurdle is just sheer complexity. Trying to describe a hardware circuit in a language like Verilog is notoriously painfully difficult. It's a completely different way of thinking than software programming, and it's what has kept FPGAs in the hands of a small group of specialists. But that's finally starting to change.
New software frameworks are now bridging this gap. Tools like FastFlow are being designed to automate all the really hard parts of programming FPGAs. You basically just describe the flow of data you want, and the tool automatically generates all the complex low-level code for you. The result? A 96% reduction in coding effort. That's just a massive leap forward.
And this slide shows you exactly what that means. On the right is the old way: complex, messy, manual code. On the left is the new approach. It's so much simpler, so much cleaner. But here's the crucial part. You get the same incredible performance, but with a tiny fraction of the effort. This is what's making FPGAs accessible to a whole new generation of software developers.
Which really brings us full circle to this powerful idea from the computing pioneer Alan Kay. For decades, we thought of software and hardware as completely separate fields. But as we've just seen, those lines are blurring completely. The absolute hardest problems in software are now being solved by designing custom hardware. The future isn't just about writing faster code anymore. It's about building the absolute perfect machine to run that code on. And that, well, that changes everything.